So we have been looking at backtracking. So in backtracking, we systematically search for a solution one step at a time, and when we hit a dead end, we undo the last step and try the next option. Now in the process of doing backtracking, we need to generate all the possibilities. For instance, remember when we tried to print out all queens, we ran through every possible position for every queen on every row. And if it was free, then we tried it out. And if the solution extended to a final case, then we printed it out. Now, if we look at the solutions that we get for 8 queens, each queen on a row is in a different column from every other queen. So the column numbers, if we read them row by row, the column numbers form a permutation of 0 to n minus 1. Right? So each number 0 to n minus 1 occurs exactly once as a column number for the n queens. So one way of solving a problem like 8 queens or similar problems is actually to generate all permutations and keep trying them one at a time. So this gives rise to the following question. If we have a permutation of 0 to n minus 1, how do we generate the next permutation? Right? So this is like thinking of it as the next number, but this could be in an arbitrary number of symbols. So suppose, for instance, we have the letters A to M. So these are the first 13 letters of the alphabet, and we treat the dictionary order of words as the ordering on the numbers. So we think of them as digits. So if we want, you can think of it as base 13. So here, for instance, is a number in base 13, or alternatively, a rearrangement of A to M in some order. Now, what we want to know is what is the next rearrangement after this, the immediately next one in dictionary order. So in order to solve this problem, the first observation we can make is that if we have a sequence of such letters or digits, the smallest permutation is the one in which the elements are arranged in ascending order. Right? So we start with A, which is the smallest one, then B and C and so on, and there is no smaller permutation than this one. Similarly, the largest permutation is one in which all the elements are in descending order. So we start with the largest element M, and we work backwards down to A. So if we want to find the next permutation, we need to find as short a suffix as possible that can be incremented. It's probably easiest to do it in terms of numbers, but let's do it with letters, right? So the shortest suffix that can be incremented consists of something followed by the longest suffix that cannot be incremented. So this will become a little clear when we work through an example. Right? So we want to find the longest suffix that cannot be incremented. So a suffix that cannot be incremented is one which is as large as it could possibly be, which means it's already in descending order. So if you look at the example that we had before, for which we wanted to find the next permutation, we find that this suffix ONMJI, these 5 letters are in descending order, so I cannot make any larger permutation using this. So if I fix the letters from D to K, then this is the largest permutation I can generate with D to K fixed. So if I want to change it, I need to increment something, and I mean to increment it, I can't increment it within this red box, so I must extend this to find the shortest suffix, namely the suffix started with K, where something can be incremented. Now how do we increment this? Well, what we need to do is that now it's like saying that we have, with K we cannot do any better, so we have to replace K by something bigger. And the something bigger has to be the smallest thing that we can replace it by. So we will replace K by the next largest letter to its right, namely M. Right? Among these letters, M, N and O are bigger than K. If I replace it by J or I will get a smaller permutation, which I don't want. So I must replace it by M, N or O. But among these, since M is the smallest, I must now start a sequence where the suffix of length 6 begins with the letter M. And among suffixes which begin with the letter M, I need the smallest one. That means I must rearrange the remaining letters K, O, N, J, I in ascending order to give me the smallest permutation which begins with M and has the letters K, O, N, J, I after it. So this gives me this permutation. So I have now moved this M here, and now I have taken these letters and rearranged them in an ascending order to get I, J, K, N, O. Right? So therefore, this means that for this permutation, the next permutation is this one. So algorithmically, we can do it as follows. What we need to do is first identify the suffix that can be incremented. So we begin by looking for the suffix that cannot be incremented, namely we go backwards so long as it's in descending order. So we keep looking for values as they increase. So I is smaller than j, j is smaller than m is smaller than n is smaller than o, but o is bigger than k. So that means that up to here we have a suffix that cannot be incremented, and this is the first position where we can make an increment. Having done this, we now need to replace k by the letter to its right, which is next bigger. Now this is a bit like insert. We go one by one. We say that k is bigger than smaller than o, so we continue. K is smaller than n, so we continue. K is smaller than m, so we continue. And now we say that k is bigger than j, so we stop here. So this tells us that the position m is the letter m is the one that we want. Right? So we can identify this in one scan, because this, remember, it's in descending order, so it is in sorted order. So we can go through and find the first position where we cross from something bigger than k to something smaller than k, and that is the position of the letter that we need to change. So it's exactly like inserting something into a sorted list. Now having done this, so we have exchanged this m and k. Now we need to put this in ascending order. But remember, it was in descending order. And what we did to the descending order was we replaced m by k. But what is the property of k? K was smaller than m but bigger than j. So ONKJI remains in descending order. So if we want to convert it to ascending order, we don't need to sort it, we just need to reverse it. So we just read it backwards. So this is just a reversal of this. Okay. So this is a concrete way in which to find the next permutation. Walk backwards from the end and see when the order stops increasing. So wherever it first decreases, that is the suffix that we want to increment. Of course, if we go all the way and we go back to the first letter and we have not found such a position, then we have already reached the last permutation in the overall scheme of things. Once we find such a position, we find which letter to swap it with by doing an equivalent of a search that we do for insertion sort. So we do an insert kind of thing, find the position, in this case m, to swap with k. After swapping it, we take the suffix after the new letter we put, namely m, and we reverse it to get the smallest permutation starting with that letter m.